So I will try. Apparently, I'm closing this event, which is quite an honor, and I will try to basically put forward some challenging ideas, things to make you think when you are in your lab, when you are in front of your computer. A few of these things I have worked on them, a few I have not worked on them, but in all of them I have dedicated some time to think about them. And what I'll try to do is to help you predicting the future. And predicting the future is very hard, especially, making predictions is very hard, especially when they are about the future. This is an old sentence, apparently it appeared in Denmark in the beginning of the 20th century, and we are all familiar with things like this. If trend X, whatever trend X is, continues, the result will be something. And we are very bad at making this kind of predictions. I will just use one example to illustrate this, which is the Great Horse Manure Crisis of 1894. At the time, the transportation in the big cities was done by horses, by horse-drawn carriages, and New York had 100,000 horses, London had 50,000 horses. They were basically the engines of the time, and the big problem of the time was that these cities were going to be covered in manure. So there was no way to remove the manure sufficiently fast out of the cities to avoid them from being covered with that. They even made a conference in New York that was to last 10 days, I think, and they gave up after 3 days because no one could come up with a workable solution to remove the manure from the cities fast enough. Okay? You know how the story goes. The New York and London are not covered in manure. The internal combustion engine appeared and basically changed our problems. Now our problems are totally different. And I'm quite sure that many of the problems, and I'm not saying this to say that they are not important, many of our problems will basically follow the same destiny that happened to the Great Horse Manure Crisis of 1894. And this leads us to the first take-home lesson. If you don't know it, remember, it's Amara's Law. And Amara's Law is an observation about the nature of technology, about the nature of technological evolution. And what Amara said was that we tend to overestimate the effect of a technology in the short term and to underestimate the effect of such a technology in the long run. Why? Because basically technology evolves exponentially, and our brains are not fit to work with exponential evolutions. It sort of make linear predictions. And in a linear prediction, you always tend to overestimate the short run, but to underestimate what happens in 30, 40, or 50 years, which is the long run for technologies. And I'll just give you one example of this, which is the number of transistors that were fabricated in a given year. And this is the curve. This is the actual number of transistors. I think you can see it, up to 2000. So up to 2000, we have been built on Earth about a trillion, a bit more than a trillion transistors were in all the devices that we had on Earth. And you can see there a very quick rise around 2000 on the number of transistors, because this is, of course, the consequence of Moore's law, which means that the transistors on a given area duplicate every 2 years. And you can see, and now you can, looking back, you can see, yeah, in 2000 a lot of things happened. Computers became more common, cell phones become more popular and more powerful, and so on. So if you go for 10 years, this is the number of transistors that were built until 2010. And you see now that actually on this new scale, of course the scale changed, but that the actual big increase on the number of transistors happened in 2010. And in fact, nothing much happened in 2000. Okay? And you can already guess what's going to happen if I project this to 2020 and of course to 2030, which is a projection and not the actual number. Every time the curve looks the same. We are always exactly in this point where things are exploding. Okay? Which means that whatever happened till now is just a small signal of what's going to happen in the next 10 years, right? And we go back. It's always the same curve, it's an exponential, and the exponentials have this strange characteristic. They always look, they are just exploding. They always look like the past. In the past, nothing happened, right? You look here, nothing happened in 2000 or 2010 or even 2020. And so this leads us to, this is what leads to Amara's law, because we cannot extrapolate these exponential evolutions. And there are lots of evidences that technology has an exponential evolution. Technology evolves exponentially. That is why it's so hard to extrapolate. So, keeping this in mind, right, and keeping in mind that I'm going to make some predictions, if you want, technological predictions, what I wanted to tell you about is what has a very strange mathematical name, which is called the Church-Turing thesis. And the Church-Turing thesis is, in a very simple expression, says that all forms of digital computation are equivalent. All digital computers, as long as they have enough memory and as long as you have enough time, they are all equivalent. The simplest computer, the slowest computer that you had 20 years ago, or the fastest supercomputer on Earth, or whatever thing you will build on the future, they can compute exactly the same thing. Just give them enough time. Okay? And the second thing is that, and this is far from widely accepted, is that the brain is as powerful as a digital computer. The brain is as powerful as a Turing machine. And if this is true, and I will present you some evidence on my view that this is true, then a CPU running a program using the electrical signals or the brain processing, doing whatever it does, they are basically equivalent. And if they are basically equivalent, we can emulate one on the other. We can emulate whatever behavior you do on one of these things, you can emulate on the other. And of course, we are mostly interested in using CPUs to emulate the brains, if nothing else, because we know how to build CPUs and we don't know how to build brains. Okay? So, just let me take you briefly through the story of computing, and this is very, very briefly. Babbage can be, even though there were machines by Leibniz, Babbage is usually viewed as the father of computing because he conceived of a machine, which was the analytical engine, which was actually the second version of a machine he had, the analytical engine, that it was a mechanical machine, purely mechanical machine, not even electromechanical, purely mechanical with cranks and levers and so on. And this machine, if it were ever built, will be equivalent to a Turing machine, will be equivalent to any modern computer. Of course, slower, forget about speed for now, slower but equivalent. He never built the machine, but a friend of his, Ada Lovelace, who was the daughter of Lord Byron, she wrote a lot of programs for this machine. She translated an interesting paper by Menabrea from French to English. She added a few notes. The paper had like 7 or 8 pages. The note had like 20 or 30 pages. And on the notes, she describes how the machine can be used to compute a lot of things. But she also wrote a few things that are even more interesting than the programs she wrote. The programs, by the way, that was the first time anyone wrote a program, right? She was the first programmer. Nobody had ever written a program before. She wrote a number of them, very nice programs, very complex ones. Go and read the original article by Menabrea and Lovelace. It's a lovely article. But on the notes, she also understood a few things more. She said things like, she wrote things like this, that the machine can work not only on numbers, but can also work on other things, for instance, on music, whatever can be expressed by the fundamental science of operations. So she understood that the machine was a general purpose machine. It could do anything that involves symbol manipulation. Go forward 100 years, you need to go forward 100 years for Alan Turing to come up with his Turing machine, which is the universal model of computation, and also with the Turing test, a test for AI, where you basically, you know the test, I don't need to go into detail, where you basically hide the computer and the person behind the wall, and if a person here cannot distinguish the computer and the person, then you have to recognize that the computer is intelligent. And of course, Turing made these fundamental contributions in a purely theoretical way. He also had work on actual machines, deciphering the ciphers of the Enigma machine, but his most important contributions are the article where he presents the Turing machine, and then a 1950 article where he discusses and addresses AI. And of course, we have technology. Technology was made possible by the invention of the transistor by Bardeen, Shockley, and Brattain. And once you have the transistor, all these wonderful ideas of Babbage, of Ada Lovelace, of Alan Turing, of Alonzo Church can be actually implemented. You can start to have actual computers. On the brain side, we also have a long and interesting story. But it was in the 17th century that Thomas Hobbes described on very, very clear terms on the Leviathan that to him, the brain was just a computer. He wrote something like this: the brain does nothing else but conceive a sum from additional parcels or a remainder from subtraction. It's a very, very clear distinction that to him, the brain is just a computer. It performs additions, performs subtractions, and also multiplications and divisions. This is, to me, amazing. I mean, in the 17th century, we did not even have any idea how the human body operated, much less the brain. Most people did not even know that the brain was an important part of the anatomy, so it was considered sort of something irrelevant. And to me, it's quite remarkable that they had this clear vision. But of course, the clear vision had no immediate consequences because there were no machines, there were no computers, you could not implement any of that. Then Darwin, 200 years later, basically, it did not describe exactly how the brain works, but it told us how brains appeared. And that is about the same. It told us how brains were built by evolution over the course of 4,000 million years and 4 billion years. And this was a fundamental contribution. It's on his books. It tells us how the brain evolved. Even so, it was only on the beginning of the 20th century that Ramon y Cajal understood how the brain works. He made these wonderful drawings of the cells in the brain. And there were a lot of discussions whether this was multiple cells or just a cell. He was right in the end. And then, already in the 50s, Hodgkin and Huxley described the electrical behavior of neurons with the Hodgkin-Huxley model that is used until today. So Hodgkin and Huxley proposed, experimented, and derived the electrical model that corresponds to the neurons. And also you have these two streams of knowledge converging, and they are converging basically now. It is today that neurosciences and computing are converging in such a way that neurosciences reinforces computing, computing reinforces neurosciences, and all of this, you can call it artificial intelligence. I use a more general designation. I'd rather call them digital minds, on the idea that we can have minds that run on a digital substrate. And there is a third one, which I don't have time to go, which I call neuromorphic computing, but on the two extremes, you can have what I call synthetic minds and natural minds. Okay, natural minds are ours, but they can also run on a digital computer. Synthetic minds are different. Synthetic minds are basically what we call in general artificial intelligence. This that we are trying to achieve by running programs that have very little to do with what the brain does. What is exactly artificial intelligence? Well, the word is used today to mean many things, and sometimes it's probably overused. But I made my own classification of AI in these three areas. At the center, we have the technologies, right? We have search and optimization, things we have been working on this for decades, since the 50s, on algorithms like alpha beta search and so on, and many optimization algorithms. And they are an important part of the body of knowledge that is AI. Then we have a lot of work on knowledge representation. How do you represent knowledge? How do you put all of this together? But probably more important, and certainly more important today, is what is called machine learning. Machine learning, you had talks here about this, and I will not spend your time on this. But the big picture is this. Those are the techniques that made AI today. And what are the applications of AI? Well, the first one is data analysis. The first big R is data. What is data analysis? Probably 90% of the economic value of AI today is in data analysis. Everything else is mostly talk, right? But it's important. But the really important things today in economics, when you discuss Facebook, when you discuss Google, when you discuss big data, when you discuss data mining, all of that, we are talking about data analysis. These have many applications, you know about it. Sales and marketing, of course, but also on process optimization, drug and treatment discovery by running through big databases of molecules and compounds and so on, analysis of social behaviors, financial analysis. All of this is data analysis, is things that you probably not do it with a human, so there is no human that is willing to go through 1 million records to see whatever pattern is on those records. is not really stealing jobs from humans in most cases. You are doing something that humans will not do anyway, and is very, very important. And if you want to sell this to a company today, probably you should be on data analysis somewhat, probably. But there is an important area, which is let's use the same sort of technologies to replace human jobs, to do things that today require a human to be done. Like telemarketing, right? It's fairly easy to use natural language processing. It will be done in a few years to basically replace telemarketers or anyone that calls you on the phone and tries to sell you something, or maybe just answer your calls on a call center. Driving, of course. Driving is typically a problem that can only be, is a task that can only be done by humans, will probably most likely be done by machines not many years from now. Let's say 5 to 10 years, we'll have fairly autonomous vehicles. Then, of course, you can have all sorts of other things that now require humans. Personal assistants, right? We have Alexa at home, and the kids don't live without it, and when Alexa is down, they don't want to stay at home because they are alone. So this sort of artificial persons that interact with you. Legal analysts, there are already a lot of programs that do the work that a legal analyst does by looking at the contract, identifying issues, and so on. Radiologists, anything in diagnosis is basically possible of being automated without much difficulty. In some problems, the best diagnoses are already made by machines instead of humans. And the number of problems where this is, the number of fields where this is going to increase is large. And then you have the Holy Grail of AI. What is the Holy Grail of AI? None of these systems, not the data analysis on the top, not these ones, are flexible systems. They do one thing and one thing only, most of the time, right? If you want something that knows how to drive a car and also knows how to translate from English to French, well, you have to buy two systems. There is not one system that knows how to drive and knows how to translate, or whatever, right? These systems are special purpose, specific purpose, do only one thing. What we would like, and by we I mean the AI community, like to have is to have some system, some algorithm. Pedro Domingos called it the master algorithm that learns how to do something like us, right? This is strong AI. This is the idea that you can have a machine that is so flexible that it can get to human-level intelligence. It can learn how to drive, it can learn how to make a medical diagnosis, it can learn how to write a poem or to play piano. We are no close to this, no, we are not close to this. We are still very far from this. We don't know. We don't know how the brain does this magic, how the brain has this flexibility. We have no idea. But we are still working on this, and maybe it will happen this century. Such a system, of course, will be very flexible and adaptable, and the possibilities are endless, right? If anything that a human can do can be done by a machine, I mean, we can do anything, right? At least that's what we like to think. So I think you had, and you know about machine learning, so I'll not spend much time on this, but let me just give an idea that may be useful if you want to explain machine learning to people that don't know what it is. Maybe you can use this to, your friends at home that don't. So, in traditional programming, we do this, right? You have an input, a programmer, usually a computer scientist or some guys that knows how to program, writes a program and the computer generates the output. This is the way computers have worked for decades since they were invented. Machine learning turns this thing on its head. Machine learning works in another way. Basically, what happens is that you give it the input, you give it the desired output, and the computer generates the program. Much better because you don't need a programmer, right? Programmers are crazy guys, difficult to work with, they are expensive, hard to find, so lots of advantages in not having programmers. But there is one more advantage, is that in many cases, we don't know how to write a program. We don't even know. Even if you had a bunch of good programmers, we don't know how to write a program. Let me give you an example, driving. Driving is something very easy, right? You have one camera, the input is one camera, let's say 1 million pixels on the camera, and you have to generate two real values on the output. The angle of the steering wheel and the pressure on the brake or accelerator, right? Positive accelerate, negative brake, right? Two numbers. So when you are driving, you are actually converting, let's say, a 1 megapixel image into two real numbers. It's sort of underusing a brain that that is so powerful. This is what we do. So it should not be too difficult to write a program that takes as input a 1 megapixel image and generates 2 real numbers. This is all it takes to drive. Yeah, I know, some of you are saying you still have the gearbox, right? But as you know, the gearbox works by itself if we run. So it should not be very difficult. It turns out it is very, very difficult. It's so difficult that we were never able to do it. We were never able to write a program that takes as input the image you see on the windshield and generates the desired output. It's simply too difficult. There are too many things on the image. You need to have a model of the world. It's quite a mess. But on this way, you can do it. It's very easy. Just sit a driver, a human driver, see what it does, is the output. The input is the camera, and generate a program that does what the driver does. So we can generate a program using machine learning that we could not program from first principles, that a programmer cannot do. And this is the real power of machine learning. There is some miracle here, right? How do you do that? Well, you know how it works. There are many ways. I will just talk about one, and very quickly, because I know you know about this. Neural networks, they are basically linear models that vaguely model the behavior of a neuron. A neuron does something on the inputs, adds them together, and then generates an output. And mathematically, this is just a linear separator on the space. If it's 3 dimensions, it's something like this. And then if you put lots of neurons together, each cycle is a neuron. If you put lots of neurons together, they can perform useful computations. And if you put there the right weight, then they do that mapping from input to output that you want. So this is the program that is generated by a machine learning algorithm. And it turns out that we know, in general, how to adjust these weights. So we know how to generate the program. We know how to generate that program that we don't know how to code, which is quite amazing. There are other ways to do machine learning, but this is the most flexible, the most important one these days, and probably never say what's going to happen tomorrow. 10 years ago was something called support vector machines, but still has the added advantage that is vaguely inspired on the behavior of the human brain. And if you do this, and you do this with what is called deep neural networks, it turns out that the first layers, for instance, if you are doing face recognition, the first layers just recognize a few elements in the input, few features, and then the second layer combines some of these features to get prototypes of eyes and nose and so on, and the third layer gets prototypes of faces, and you put all of this together, and then you get the program to, in this case, to recognize faces. But it could be done to drive a car or to do something else. And there is an interesting thing, is that when you look into this, the human brain also does something like this. The first layers of the cerebral cortex also do this sort of feature detection, and then as you move up in the layers in the cortex, it does more complex feature detection, and then as you move up on layers on the cortex and on the brain, we don't know what it does because we get lost, but it's very likely that it does things like this, combining features in strange ways. And when you put all of this together, what you obtain, if this works, is multi-layer perceptrons, deep neural networks that can be trained. In this case, is a simple illustration of one of these deep neural networks that was trained to recognize handwritten digits that can be used, for instance, to read and scan zip codes and send the letters to the right place. And this is the sort of technology that is all the rage today, and that is at the basis of all the enthusiasm that exists today about AI and machine learning. And there's one more trick, and I will share this with you because you may not all of you know about this. You don't even need to do on this way, which is present the input and the output at the same time. There is something called reinforcement learning, where you can actually show a series of inputs and just show the desired output right in the end, right after some time, and then you get the program. This is called reinforcement learning, and this can be used, for instance, you can imagine that the computer can learn how to drive a car by itself by just doing whatever it wants, and then if it crashes, you say, that was wrong, and if it gets to the right place, you say, that was right, okay? Not very practical with real cars. You don't want to crash 1 million cars to get a car from place A to place B, but you can do it on a simulation. So you can use reinforcement learning to tell computers how to learn, even from delayed rewards, a technology that is very important in some cases, and in particular is important in two cases that I want to talk to you about. See if this works. This is a robot. It's trying to balance that pole. In the beginning, it's not doing anything interesting, but now, after training, using reinforcement learning, it learned how to balance the pole just by itself, right? And there were no equations of mechanics there. It just learned how to balance a pole like that. And this same technology can be used, and was used, for instance, to learn how to play Go, and is used in other applications. Go is a particularly interesting case, because in the first version, which is called AlphaGo, that the program that beat the world champion was trained on games played by humans, on tens of thousands of games played by humans. But in the second version, AlphaGo 0, the program just learned by playing itself and became better than any human, became better than the AlphaGo that was trained with human games, and in fact discovered strategies and tactics that were not discovered in 3,000 years of human games. So this is quite impressive to me. It's just a game, it's a very difficult game, and it's a game that in just a few days became better than all of humanity knowledge combined. And of course you have driving. This is a Tesla. If you never drove on a Tesla, you should. Is impressive. The acceleration is also impressive to see a car driving by itself and making a fairly good job at it, even learning to drive on the style of the driver that owns the vehicle. And this is a slightly different case. This was a program by IBM, Watson, that was fairly coded for a specific purpose, which was to play this game, which is a riddle game. But even though it is a special purpose program, it made a very strong impression, because in fact it can understand these riddles, it can present the results, and again it beat the best humans. So this is what I wanted to tell you about artificial digital minds. Okay? And you have heard a lot about this, but maybe you have not heard so much about what I call natural digital minds. And what is a natural digital mind? It's based on the idea that you can perform whole brain emulation. What is that exactly? Well, first of all, let me go through an analysis of the comparative computational power of the human brain, and in this case of an Intel Core i7. Okay? The computation was first made by von Neumann in 1957. The computers were slightly slow then. Right? The brains were pretty much as good as today. Actually, von Neumann was probably even better than most of today's brain. But the numbers, if I get the numbers with today's computers, the numbers are this. The human brain has about 10 to the 11 neurons, something close to 100 billion neurons. And each neuron has between 10,000 and 100,000 synapses, which means that overall, tops, the brain will have something like 10 to the 15 synapses. I did not tell you what a synapse is, but basically a synapse is a chemical mechanism to transmit signal from one neuron to another. So the electrical signals from one neuron to another. This is more complex than this, but the basics is this. The electrical signal is transmitted from one neuron to the other by a synapse that releases some chemicals. So a synapse it works very much like a transistor, which transmits the electrical signal from one wire to the other. And the synapses work in milliseconds. The neurons and synapses work in milliseconds, work in the kilohertz range, which means that a brain, you probably never thought about it this way, does about 10 to the 18 operations per second. An operation is just turning on or off a synapse, a signal going through a neuron firing and going through to another neuron. So your brain is an exascale machine. Those are the good news, right? Where an exascale, where the operation here is just on or off, right? Transmit the signal, do not transmit. But an Intel Core i7 has something like 1 billion transistors, but it works in nanoseconds. So that means that an Intel Core i7 is also an exascale machine. Here we are talking about these elementary operations. And transistors and synapses, I think this comparison is very fair. Von Neumann made a comparison. I think it's very fair. They have, of course, complex behaviors. Maybe you need a couple of transistors to simulate a synapse. Maybe one is enough. But this comparison should humble a little bit, because it means that And contrary to what probably you have been told all your life, that the human brain is not immensely more powerful than a computer. It's probably just about as powerful as a standard processor. So why is it then that computers are not smart and we are? Because we don't have any idea on what program to run on this to make it behave like that. If we knew the program, then probably we can run your brain on your laptop, which is quite an interesting idea if you think about it. But we don't know. We don't have that program. We don't know how to get there. We don't even have any idea how to work towards getting there. So we have to go around it, because to have that, you'll need to know how the brain works in very minute detail, and we don't. To go there, we need to go around. And around is how, well, we can simulate the brain. We can emulate the brain. We know how neurons work, since the work of Hodgkin and Huxley. We know they are electrical circuits. We can simulate these electrical circuits. This is a simulation I made 40 years ago in my PhD thesis on when I first came across these models. You can characterize real neurons by putting a probe there and injecting current and doing this. And then you can recreate in very minute detail the electric model to have exactly the same behavior as the one that you observe on the real neurons. Not only can do this, we have done this. There are thousands, probably hundreds of thousands of neurons, in rats mostly, that have been characterized. We have electrical models for these neurons. So what we can do, we can put all these electrical models together, and then we can simulate them on a computer. But this, of course, is inefficient, right? It's not as efficient. It's like simulating a storm on a computer. It's very inefficient. You need days to simulate maybe a few minutes of a tornado or something. But this is the best we can do. And if we do this, and people have done this, they have done this for thousands of neurons, even in some cases for millions of neurons. If you do this, for instance, this particular simulation I was referring to, it used 12,000 neurons. You run on the Blue Gene P, which is a 14 teraflops machine, and it took about 3 hours for 4 seconds of one small cortical column, just a very small part of a rat brain. And this was about 3,000 times slower than real time. When I made these slides, the Sunway Taiwolite was the fastest computer on Earth. It's no more. Now there is one in the US, which is twice as fast, but it doesn't matter. The numbers don't change much. If you run the same simulation on the Taiwolite, it will run about real time, 2 times faster than real time. So if you use the fastest computer on Earth, it could simulate a cortical column, which is about 1 millimeter by 1 millimeter by the thickness of the cortex. You could do it on real time, which means, of course, that you need a whole bunch of computers to scale up to whole brain. If you use the Sunway Taiwolite computer to simulate the whole brain, if you had the network, which you don't, I'll go into that, then it will be about 3 million times slower than real times, and the energy will be even worse. So this seems to show that we cannot emulate a brain on a computer. It's too slow. This mechanism is too slow. But of course, not everything is against us, right? Because we are still working on fastest computers. Moore's law is still going on. We can have models that are smarter and can create abstract and hierarchical simulations. So people are working in this. This is very difficult, but it's not impossible. We know how to do this, right? We don't know how to do a quantum computer with 3,000 bits. We'll get there eventually, we don't know. This we know how to do it. It's just too hard. It's like sending a ship to the next star. We know how to do it, we just don't have the resources. It's too much. And, but I told you, yes. But we don't even have the network of the brain. We'll have to have the electrical network of the brain. And if we want to have the network of the brain, then we have to reverse engineering the brain. And there are a number of ways we can do this. So the simplest way is to use imaging techniques. Let me see. Is to use imaging techniques. Those are images obtained using magnetic resonance. And you can get these wonderful images of the connections between the different regions of the brain. And you can have even more detailed information about the behavior of parts of the brain. But we are limited to things that are about a cubic millimeter. It's too big. The neurons are much smaller than this. So a cubic millimeter does not help you much. It's not enough. You don't have enough detail to obtain the brain network. If you want to obtain the network of a brain, then you have to kill the brain. You have to slice it. What you do, you slice it. You slice in very thin slices, micron-thin slices. Then you put this through an electron microscope. you get this detailed image that go down to the very minute details, and we are zooming in. This is a slice of a mouse brain, and as we zoom in, we start to see the neurons and the synapses and all the structures, and then you can use computers to mount these images, these very detailed images of the neurons, and obtain the three-dimensional structures of the parts of the brain that have been imaged. And the final result is this, is we get the network of the brain, and we get the connections between the neurons, and at least conceptually we can get the models. I say conceptually because there are still many things that are hard to get, and I see here people that work on this area. We don't know the strength of the synapses. There are many things, but in principle, at least we can get the network of a brain, and this has been done for very simple animals. I'll show you one in a minute. But we get, this is the sort of detail that you can get with these technologies. Of course, there's the slight disadvantage that is 100% fatal for the brain, right? Not a very good success rate, but still. But still, it led to some interesting results. This, as I told you, C. elegans is a small worm that has been, its brain has been reverse engineered, has only 302 neurons, all of them are the same, and people are still working on building a simulator for this, and we still don't have this. Even this is very hard, so keep in mind I'm talking to you about things that are very, very hard. Still, there is a company, Nectome, that proposes to basically conserve your brain and keep it in such a state that you could be revived a few years from now when we have the technology. They make no claims about the restore process. They are just for now selling the backup, let's say. It's a one-way process. It's an MIT-based company that is working on this, which has been actually under fire because they are selling something that they don't know whether it will exist. And then there are simulations. This is that 12,000 simulation I told you about the cortex, a cortical colon on a rat, and this is another simulation of the thalamocortical system. So we can do this. We are, of course, very far from being able to emulate a complete brain, but interestingly enough, there are people that believe that the easiest way to get us to strong AI is to emulate a brain. I'm not one of those persons, but there are persons that argue that it's so hard to understand how our brain works that most likely the simplest way to have strong AI, to have human-level AI, is just to emulate a brain. So I'll leave that to you. We'll have time for a couple of questions. Let me just present to you a few objections. Interesting, most of these objections were treated by Alan Turing in his 1950 paper, and the answers that he gave then are the same today. They did not change. The first one is very interesting. People argue, no, man is the sole owner of an immortal soul. No machine can ever have one. Alan Turing had an interesting response to this. I'm no good in theology. But it seems to me that you are putting a lot of restrictions on the powers of the Almighty. Certainly, he can give a soul to a machine if he decides to. Who are you to say, well, the Almighty can give souls or not give souls, right? Then there is the consciousness objection, which is a slightly different version of the same, in which says, now, intelligence can only come from consciousness, from self-consciousness, and no machine can be self-conscious. I don't have time to go into this discussion, but you can read my upcoming book where I discuss this a little bit, or you can ask questions after this. There is, of course, always this argument. This is too difficult. This is such a difficult task that we'll never make it. Making predictions, remember at the beginning of the talk, making predictions about the future is very risky. Then there are a few interesting questions, objections about the support. These objections vary, but basically they go something like this. Brain uses quantum mechanisms to work. Roger Penrose was the most famous supporter of this idea, and you cannot emulate this on a computer, so you cannot reproduce. But there are variations on the topic. There is the mathematical objection, which is the brain is a continuous machine, is more powerful than a Turing machine. It cannot be emulated on a Turing machine. And there are a number of objections that are more wishy-washy, like a computer cannot create anything new. It's called the Ada Lovelace objection. A computer cannot feel love and cannot like strawberries and cream. But, I mean, to us and to the people in this room, those probably. Now, the other ones, some of these are interesting. So think about them and we can discuss. We have a few minutes to discuss this. And so I finish with a couple of speculations. And you say, as if this is not speculative enough, right? So This is extracted from a report from the European Parliament on the legal and social sciences of artificial intelligence. And basically, the European Parliament asks whether a sufficiently advanced system should be regarded as natural persons, legal persons, animals, or objects, or some new category. So addressing the question or whether we need a new legal class for AI systems. Then, of course, there is and they advocate creating a specific legal status for robots. There is, of course, a long discussion on the possible effects on the labor market of robotics and AI, but this is something that you probably have heard about and read about in many places. And then they also argue for a unique identification systems for robots, which, of course, is strongly tied to the first question. And just let me tell you about two ideas that are not new. The first one is the idea of the singularity. You probably heard about this. Is this idea that at some point technology will evolve so fast that all of society, all of technology, all of humanity will reach a point where you cannot predict, you cannot anticipate what happens past that. This idea, which was an idea also by von Neumann, which, as you know, is one of the biggest geniuses of the 20th century. And people are discussing when and if and when the singularity will arrive. And the idea of the singularity is closely tied with this idea of the superintelligence and intelligence explosion. The idea of intelligence explosion is an idea by even John Good, a guy who worked with Alan Turing, and his argument is the same. If we are designing intelligent machines, and if we can design intelligent machines that are good at designing intelligent machines, we just need to design one, right? Because then that machine will design the next one, which will be more intelligent, and that one will design the next one, and that will lead to an intelligent explosion. And as he said, this is the last the last invention we ever need to make. Then the machine makes all the other inventions because, you know, it only creates the next intelligent machine and so on. And this is an interesting idea. We like to think of the scale of intelligence as something like this, right? We are humans, we are here at the top. Bacteria, not very smart, of course. Cats somewhere in the middle, maybe a bit to the right if you are a cat person. But maybe the intelligence scale is not like this. Maybe the intelligence scale is like this, that we are actually very similar to cats, just slightly smarter than cats, and we can have systems vastly more intelligent than us. So this is the idea of superintelligence, the idea that you can have a machine that is so much more intelligent than us, as we are, for instance, more intelligent than bacteria or to cats or from monkeys, whatever you want. And of course, this has some interesting consequences because the second most intelligent species on a planet usually does not fare very well, right? At least from what we know. Being a chimpanzee is not very interesting because there is this, the most intelligent species, of course, has such a dominating position that it basically sets the world in such a way that what is this now? Oh, no. I finish with just a few reading suggestions. My favorite science fiction book on this, which is by Greg Egan, Permutation SIP. You can read the subtitle, 10 Million People on a Chip. This book by Nick Bostrom about these ideas of superintelligence. Of course, Ray Kurzweil, who is the prophet and apostle of the singularity. This is an interesting book by two MIT guys that basically address the economic consequences of artificial intelligence. This is a short-term thing, let's say 10 to 20 years in the future. The Master Algorithm, a book I strongly recommend by Pedro Domingos, who, as you know, is Portuguese and well-renowned researcher on machine learning. This is interesting. This is a special issue of IEEE Spectrum, which is the flagship publication of the Electrical Engineers Association. And this is a special issue on can we copy the brain? So these things that I told you, they are the object of a specific special edition of IEEE Spectrum, where they address these questions and discuss. This is Life 3.0, a very interesting book, which I recommend you read on, especially if you are interested on that idea of intelligence explosion. It starts with that, just the first chapter, actually is before the first chapter, is a wonderful description on how an intelligence explosion can happen. And of course, I have to put here some marketing ploy. And if you want, this thing addresses all of this. Thank you very much. Was that what I wanted to talk to you?
So we have some time for questions.
Thank you so much for the talk. It was really fascinating. Just on the last couple of slides back, you were talking about the problem or the issues with superintelligence, and I was just wondering if you personally are scared of superintelligence, and if you are, then how are you trying to control those things from eventuating?
Good question. I have read and discussed a lot about this, and I did not make up my mind. If you read this book, you'll probably be scared. So I read this book after reading several others, but so read this one. If you want to be scared, read this one, because the beginning is like the D-Day invasion of that book, Saving Private Ryan. You know, those first 10 seconds. So this book is like that. So it's like the Normandy disembark on that. So because it presents such a reasonable, such a vivid scenario of how such a thing could happen, that it looks like you are reading the newspaper. So I think it is a possibility. On the other hand, we don't know how to create intelligence systems, right? We don't know. We have no idea. We don't know how strong AI could happen, because what we do know is things that are very different: specific purpose systems, image processing, whatever, pattern recognition systems. So we don't know how to do a brain. So on one side, we are very far from knowing how to build such a thing. On the other hand, if you have imagination, you can imagine how to do such a thing. But there is an interesting argument about this. Imagine that we know that 30 years in the future, so let's say 2058, a spaceship with aliens, you know, very intelligent, very advanced aliens, is going to arrive on Earth, right? We know that. So the question is, would you just sit around and say, well, in 2058, we'll see what we do, right? I mean, we don't need to worry about that now. So if we know that in 2058 we are going to have a super intelligent machine, should not we be worrying today? Should we not be working on mechanisms and strategies to make sure that when it arrives, we are ready? That we have the right setting, that we have the right rules, that we have... Some people argue that AI researchers should work on caves unconnected to the internet, just in case they discover something that the thing doesn't get loose on the internet. This is a technique. Shouldn't we work? And there are people that have been arguing this, that just the fact that we don't know when it will arrive does not mean that we should not be working on it now. How to control it, how to set it up that it is benevolent, how to set it up that is under our control. So it's an interesting discussion. I did not make up my mind, but I have to tell you that the setting that Mark puts in his book is very, very... I don't want to tell you about the plot, because I really think you should read it. But it's very realistic, to say the least.
This is just an observation. I enjoyed your talk. I just want to mention that Jack Good, who came up with this idea of superintelligence, he was a primary consultant to Stanley Kubrick in the movie 2001:
Yes,
Space Odyssey.
he was.
With the idea of HAL, and we all know about HAL. Those of you who've seen the movie know
Yes.
about HAL having what could be called a nervous breakdown. So maybe Jack Good knew something more than we attribute to him.
Yeah. He was indeed a consultant, and probably the movie is what it is in part because of him. He died a few years ago, not long ago, actually.
Thanks a lot. There are two questions that come up. One is how you measure intelligence and how you decide, because you put a scale that felt right.
Excellent question, yeah. No, I was wrong. I should not, because this scale seems to show that I think that intelligence is a single-dimensional thing. It is not. Certainly intelligence is a multidimensional thing, at least 5, maybe 10, maybe 20 dimensions, or even something more complicated. This is just for illustrative purposes. I don't measure intelligence, and I even believe that this is wrong. So this is just to give you the idea that we cannot, at least I cannot easily imagine something that is much more intelligent than ourselves, right? Normally. I mean, if you try, maybe you can think. Imagine something that knows all the papers that were written on the world, understands all the papers and books that were written on the world, knows everything that is on the internet, has all of that, and has reasoning powers of all of this. So this will be a super intelligence, right? I mean, will be more emotional intelligence, will be more creative, whatever, it depends. I mean, Google is fairly close to a super intelligence in some respects, right? If we are just talking about answering questions, Google is much more intelligent than I am. But you're right. I mean, I did not put this to mean that there is a specific measure for intelligence, and even the normal measures for intelligence are things that are very debatable. I don't think they are good measures of pretty much anything.
Is it on?
Yeah.
And the other question is, of course, how you measure consciousness. I know that you said you're not going to talk about it.
That is more interesting. That is more interesting. So consciousness is this, to me at least, fascinating thing, right? What is consciousness? Consciousness is something is conscious. This is the best definition I found. Something is conscious if you can imagine what is it to be that something, right? So you can imagine how is it to be a horse, right? This is a thing that makes sense, right? You can imagine, I mean, maybe not very well, but you can imagine how is it to be a horse, right? But you cannot imagine how is it to be a mug, right? Doesn't make sense, right? To be a mug doesn't make sense. Mugs are not. I mean, they are objects, but they don't have an internal perspective. So consciousness is something that gives whatever being has it an internal point of view. This is the usual definition of self-consciousness. Now, the interesting question is, who is conscious? Who has this sort of self-consciousness? So the radical view is this: I am the only conscious entity on the universe, right? You look like conscious, but I don't know, I cannot tell, so I am. This is the solipsistic view, right? All I know is that I'm conscious. For all I know, you can all be robots that are not conscious, right? So this is the most radical approach. Most people don't take this stance. So most people are a bit more reasonable and assume that, well, other humans are probably conscious, most of them at least, right? So, but then you start, the things get, so, and what about dogs? Are dogs conscious? Do they feel? Do they have an internal point of view when they run to you when you get home? And difficult, right? So, and if dogs are conscious, probably chimpanzees are conscious, probably dolphins are conscious. Even a strange animal that probably is conscious is octopus. Octopus separated from us 600 million ago, and they evolved a separate intelligence. Actually, they have 9 brains. So octopus have a central brain, then they have a brain for each arm, and all the brains report to the central one, but they also work by themselves. And there are a lot of tests that show that octopus are probably conscious, at least up to some level. And they separated from us 600 million years ago, which, if they are indeed conscious, means that consciousness either evolved before that, very unlikely, or else evolved independently after that. Right? So my view, but this is very debatable. I mean, any guy you ask will answer differently. My view is that consciousness is a progressive thing. Probably started happening hundreds of millions of years ago. It exists at least in mammals, in some birds, and probably in octopus and the family. But there's a big discussion about this. There's even people that argue that human consciousness only appeared 3,000 years ago, that before that humans were not conscious, because consciousness is only required when you have to think on the subjective viewpoint, when you have to think, what is it thinking? Before that, societies were not complex enough for that. And so this is a book, I'll tell you the name in a minute. So, I mean, it goes, the opinions go all the way, right? From consciousness appeared 3,000 years ago to consciousness appeared well, the most radical opinion I know is consciousness appeared 542 million years ago with the Cambric explosion. So, as you know, there is if you want to have your theory, there's lots of space to put it there.
So,
But it's a very interesting question. A final point. I think most people agree on this. Consciousness has to have some external effect. Otherwise, it will not have evolved. So the animals, us or whatever, they have to behave somewhat differently if they are conscious or not, right? And if it has some external effect, then you can test for it. We don't know exactly how, but you can test for it. So the possibility that you have a person that is not conscious and behaves exactly like another person who is conscious is not a realistic one from an evolutionary point of view. Because now, of course, you can imagine that consciousness does not have external effects. It's just a side effect of evolution, which means that you can have persons that are not conscious, like you. Maybe you are not, right? Maybe just. But I personally believe that consciousness has an external effect because otherwise it would not have appeared. So it's a primary result of evolution and not a side effect of evolution. There are a number of books on that. I mean, there are probably hundreds of books on consciousness.
Yeah, I also have one. We heard here during this week about neuromorphic computing, quantum computing, chemical computing. In your opinion, what's the most promising of these technologies to get to the superintelligence? Or is it just a faster i7 processor? Where do you think we're going to go?
I used to have a longer version of this presentation where I had three types, right? I had AI, synthetic systems. I had this all brain emulation, and I had something on the middle which I called neuromorphic computing, which is a system that is trained and evolved on the same mechanisms that the human brain works, but is not a copy of the brain. So I did not have time to go through all, so I removed this middle. But I still think it's an interesting idea, which is because this idea of reverse engineering the brain, as you can see, has many technical challenges. On the other hand, maybe there are a reasonable small number of principles that govern the behavior of the brain, that govern the evolution of the brain, and maybe those principles can be simulated on a machine. So not all brain emulation, which, as you can see, is a copy, right? You copy a living brain. It's something that is evolved or is created on the image of a brain, but is not an actual brain. I think that I will put my money on that as a good possibility, because I know, even though many people argue that all brain emulation is possible, not only in principle, that we have now, today, all the technologies that we need for all brain emulation. We don't need anything new. We just need to scale existing things, right? Unlike quantum computing, unlike strong AI. We don't know how to create strong AI. We need some new idea. To do all brain emulation, this is actually the argument of Nick Bostrom. We can do it today. We have everything. We have the microtones to slice the brain. We have the microscope. We have the simulators. We have the neuron models. Maybe. So those are opinions. But still, my money will be maybe on the middle, which I did not put on but you get the idea. This is a spectrum, right? This is a spectrum from totally synthetic artificial to the emulation of the natural to something in between.
Well, this is just a comment on semantics. Well, as scientists, I think we have added responsibility to express ourselves correctly, regardless of the audience, be it scientific, or specialized, or general. So I would think that terms such as miraculous or magical are not very adequate in these sort of presentations. The same way that in cosmology, for instance, we have dark energy or dark matter to express our ignorance of the things. Maybe here we could use similar terms to denote that.
So you are referring to my term of the magical...
Exactly, because you're not the first person that I've heard those terms from.
Well, it's mostly for
yes.
illustrative purpose.
Still,
of course, it's not magic. I think
I
refer to magical in the machine learning algorithms, right?
Or miraculous or whatever. There's a miracle, magic.
Miraculous, I don't remember.
Or miracle. Anyway, those are common terms in machine learning and AI, talks, and I think they're very, contradictory, for scientists.
I hope I did not give the impression that some of this is miraculous. So
yeah, I mean.
I hope I did not. So I apologize if I did. Yeah.
It's okay.
It's fairly hard science, most of it, actually.
I do have a comment, and has nothing to do with quantum mechanics or entanglement. It's my reaction to the artificial intelligence and the old question, who's afraid of artificial intelligence? And for me personally, I'm not that much afraid of artificial intelligence as much as I am from natural stupidity, okay? And by natural stupidity, I mean, if you look at the world, how humans treat the planet, pollution, and stuff like that. So this is just my final comment. Before we get scared about artificial intelligence, perhaps we should be more scared of our own natural stupidity. And this is just a small comment.
Yeah, Pedro Domingos he has a very interesting talk, and he made a very interesting comment on that direction. Yeah, Pedro, so as I think I told you, I'm balanced on the dangers of AI. I don't lose sleep at night, but I don't discard them as totally irrelevant. Pedro Domingos does not believe them. So Pedro says, this is bullshit. I mean, we are centuries away from creating intelligent systems. What we have to worry about is stupid systems, at least AI systems that are not intelligent enough. And he gives us examples, and the examples are good, is that imagine you create a system that controls, I don't know, the energy grid and tries to optimize it to obtain some final result. And if it's not smart enough, you may decide to shut down the grid to avoid CO2 emissions or whatever. So he's more worried about systems that are not smart enough to take care of the tasks they are given than of systems that run amok and then try to challenge humanity. But again, as I said, I like Pedro Domingos a lot. His opinion is not unanimous. For instance, Stuart Russell, who is a big name in AI, as you know, professor from Berkeley, he has written the textbook on AI that every school uses. He recently, in the last 5 years or so, he has taken very aggressive stances on this question that we should understand the risks of strong AI. He has taken, and there is a number of podcasts you can hear from him, Stuart Russell, and I mean, he's not a guy that doesn't know what he's talking about, right? He's probably the biggest name in AI. So I think it's interesting to listen to different sides on this thing. That's why I don't have a final answer to that.
Maybe last question. Okay.
So one of the main things I keep thinking about is how can we actually include intuition into the whole equation? What are your thoughts about that? Because one of the main things that we can do that machines cannot yet do is to solve problems based on intuition, right?
Actually, people sometimes make that question with intuition, sometimes with emotions, and sometimes with other different properties of human thought. I think intuition, there is a saying that intuition is the highest form of intelligence because it's the intelligence that you cannot formalize. And actually, what we have learned about AI is that a few things that look very hard are actually very simple. Demonstrating theorems is fairly simple on the scale of things. Recognizing things on a scene is fairly hard. And solving things by intuition, like you said, is even harder because we don't know how to do it. For instance, factoring in intuition in a Go game or in a chess game is very difficult because the masters cannot explain to us what they do. On the other hand, if you know, and there is a movie on Netflix about the Go world competition. It's amazing to watch. And in the end, the human champion was discussing the intuition of the machine. So how could he know that that particular stone placed on that position on the 20th move has an effect 300 moves later? So I don't think intuition is very different from other forms of intelligence. It's just higher on this scale. And as we move higher and higher, we'll get to some sorts of intuition. Maybe not all of them. Maybe not all of them. But I mean, of course, as I said, human intelligence is a very big pyramid or cylinder or whatever, with some low layers that are fairly easy to get, some middle layers that are fairly hard, and probably some high layers that are very, very hard to get, and it'll take a long time. On the other hand, maybe there is some general organizing principle on the brain that some guy will discover, and then you can just create a brain on a computer like that. It could happen tomorrow, right? If there was a conference on AI, and the guys from DeepMind were there, and some guy was placing a bet, can you tell us something that a machine will not be able to do in 10 years? And it took them a long time to come up with something that they were quite sure that the machine will not do, because the guys from DeepMind were there, and if they knew that they cannot do whatever, write a motto, then the DeepMind guys will just attack that problem just to prove them wrong. So in the end, they come up like something like a robot that can fold clothes removed out of the machine. So apparently it's very difficult because you need to do the image processing, understand that mass of clothes, and so on. Apparently that is considered to be one of the hardest tasks to do by robots, but I don't know.
So I'm actually going to abuse my position as organizer and ask one more question, which I think it relates to the topic of the school, and that's why I think it's important to have Arlindo's opinion on this. One of the trends that we've been seeing in the last few years is that a lot of the research on AI is, as you pointed out, done by groups which are in the industry, which are privately owned, and which can develop technology in a way that, in a certain way, it's not controlled by us. It's according to their own goals. If AI is truly this revolutionary technology that can open many doors, good and bad, how do you see the role of the universities and academia when the big groups are being bought by companies, the big groups in academia are being bought by companies, and most, or at least a significant amount of the results of AI are being produced by industry?
Yeah, excellent question. Actually, there's something that I usually tell, but I did not tell today, I think is, why is it that those companies are so proeminent now? And why is it that AI is having all this good time this year? I mean, AI has had many winters, many springs, and so on. There are three reasons, in my opinion. The first one, we have slightly better algorithms. And I say slightly because none of that I told you about, backpropagation, deep neural networks, is really that new. Most of those things have 30 years, just a few details. I mean, the basics were there. Then there are a few changes, but the basics were there. But the algorithms are slightly better than they were. The second is that we have data. We have lots of data. And we can to train these systems, we need billions of data points. And for the first time, we have the data. And third, we have the computing resources to process all this data with this algorithm. So this is three components. And of course, there's a fourth component, which is human brain power. And it turns out that the companies you are referring to have all these four. They have all these four things because the algorithms are fairly public, they have the data, they have the computing power, and now they have the people. And the universities do not have exactly all this. They have more difficulty with computing power, they have much more difficulty with data that is proprietary, and even the human brain power has been running away from the universities. So I am not overly optimistic that the universities will keep playing the important role that they have played since the 50s on AI. I feel that, and you see it now, that many innovations come from private, some from fairly small companies. But of course, we have many people here that work at university, and we have young, newer generations. I don't think these companies can vacuum all the human brain power that is appearing every day. So maybe there will be enough people so that we have evolution in the companies and also in the universities. And I certainly hope that educational initiatives like this one and like others, we had the machine learning school in Lisbon, which was a great success, like the 8th great success. And I think these initiatives, and of course the courses, the degrees and so on, I think they play a role. And if you have enough people working on this, I'm hopeful that we'll be able to also make contributions outside of the companies.
Thank you. Let's thank our speaker.